Hey everybody, I want to talk to you today about probability distributions and a little bit about probability as well. We're not going to do too much with like classical probability. We're not going to be rolling dice or picking cards or anything like that. But we do need to understand the basic concept of probability to understand statistics. I don't know if I've said this before, but statistics is basically probability plus calculus. Like if you take probability and add calculus to it, the thing you get is statistics essentially. So I want to talk about probability distribution. So the first question is, what is a probability distribution? And I think I put it in my second bullet point here, but it's a list of every possible outcome of something that you're doing and all the probabilities that go with those outcomes. Now, I put list in quotes because we don't always like list them out. Sometimes it's in the form of a graph or a picture of some kind. Those are actually the most common forms of probability distributions that we'll be using. So you still want to think of it as a list of all the possible outcomes, but it's going to be in picture form a lot of the time. And the other thing we really want to know about probability distributions is that everything adds up to 100% or 1. We're going to use 1 a lot of the time, but you can think of 1 as just meaning 100% if you prefer. It's the same either way. You're literally just moving the decimal one direction or the other. Yeah, so let's see how these work. So I've got a bunch of examples, and we're just going to kind of go through them, and I'm going to sort of explain probability distributions by showing you probability distributions and using them rather than talking at you too much. Before we get started doing that, though, I want to talk about probability. Like I said, we're not going to be doing any of the classical probability, dice rolling, coin flipping, card drawing. I'll actually use those as analogies when we get to topics 5 and 6. But basically, you just want to think of it as how likely something is to happen. So higher probability means more likely. Obviously, lower probability means less likely. And all probabilities have to be between 0 and 100%, or 0 and 1, depending on which way you like to think of it. And that is actually a thing that we will return to a bit later. It turns out there's a particular kind of probability that we find, and it's kind of easy to get negative answers or answers over 100% if you're a little careless. And so keep in mind, whenever you are finding a probability, it must be between 0 and 1, where 0 means impossible and 100 means certain, and everything lies somewhere between there. So you can't have negative probability. You can't have a probability of like 230%. Those are not things. The other thing I want to mention is that the notation for probability, because we don't want to write in words, the probability of blank is the shorthand. There's a capital P with parentheses around whatever thing that you are finding the probability of. And that's so if I have P of event, I would read that the probability that event happens, or I would just probably read this probability of event. So let's see how we use those things. Oh, I guess I need to talk about and, or, and given first. So there are 3 common, we'll see that will run on the next page there. There are 3 common probability, I don't even know how to what I would call those, modifiers? That's not the right word, I'm sure. I'm sure there's a good word for and, or, and given, but basically things that can connect to events inside a probability statement. So for instance, the probability of X and Y, where X and Y are both things that can happen, is the probability of both of them happening together. What that means is that probability of X and Y is always less than the probability of X or the probability of Y, because X and Y happening together is always going to be less likely than either one of them happening independently. Like if just X happens and Y doesn't, then this isn't true, right? If X happens and also Y happens, then this is true. So it's always less likely to have 2 things happen than it is to have one of those things happen independently. The opposite is true for or. So probability of X or Y means that either X happens or Y happens, or they both do. So there is something called exclusive or, that's just one or the other, but not both, which is how English is usually which is how the word or is usually used in English, but it's not used that way in statistics. It's inclusive or unless stated otherwise, where X or Y means X or Y or both X and Y. This is always greater than, or the probability of X or Y is always greater than the probability of X or the probability of Y independently. Because if either one of these happens, then the probability of X or Y, then X or Y is true. So in the same way that both of them have to happen up here, so X and Y is always less than the probability of X and also less than the probability of Y. Probability of X or Y is always greater than or equal to, I guess, the probability of X or the probability of Y. So, and restricts things. It means that more things have to be true, or loosens things up. It means that one or the other or both is true. So this is always at least as big as the individual probabilities themselves. And this is always no bigger than the individual probabilities themselves. Okay, so there's one other one that I want to talk about, which is given. It's this vertical line here. And this is read the probability of X given Y. So this is the probability that X is true if we already know that Y is true, or we're assuming Y is true, which is a thing we're actually going to do quite a bit later. So we're starting with the knowledge or the assumption that Y is true in this case. And then within that, we find the probability of X. And we'll see how this plays out in just a second. So yes, I think that's all I want to say. I could go off on a huge tangent. There's a lot of stuff to say about this. It's called conditional probability, right? We're conditioning the probability of X on Y. But I don't want to jump into the math too much for that. That ends up being quite a bit to learn and also distracting from what we want to do. So here, I'm going to start with the example. I'm going to start with the examples here. I'm going to start with the example of a probability distribution in a table. So here I've got this probability distribution for some theoretical class, right? And so here's the grade breakdown. So in general, I'm going to let my variables be X most of the time. In this case, I've got my the outcomes for my variable could be A, B, C, D, or F, right? I'm going to ignore pass, no pass grading or anything else like FWs or anything like that. Just A, B, C, D, F, that's all we got. So I have not filled in F here because we can figure it out from context, right? We know that the total has to add up to 100%, so we can figure out what goes here by adding up the totals for A, B, C, and D, and then subtracting from 100%. So I've got 12, 35, 75, 86. So if these add up to 86%, then F must be 14%, because that is what is remaining. Straightforward. That's all I really want to say about that. We will return to this particular chart in a couple of pages. The other kind of table that we can have is one that looks like this, where we've got multiple different variables, right? So here what I've got is a table of the survey results of talking to people about what color car, or asking people what color car they have, right? So I'm breaking the results down into men and women, and then the colors are black, white, silver or gray, red, and other, right? And we can see what the totals are. And then what we're going to do is we're going to cleverly fill in the rest of the table, right? It's not super clever, but let's do it, right? And so, we're just going to treat this like a little puzzle, essentially, an easy puzzle, but a puzzle nonetheless, by making sure that the totals work out, right? So 100 men, 100 women, overall total is 200. We can figure out basically a bunch of these, right? If there were 17 men who said that they own a black car, and there were 41 total people who said they own a black car, well, then the remainder must have been women who said they owned a black car, and if we subtract, we get 24. Right? What else can we do? 45 men said they own a silver or gray car. 84 people total said they own a silver or gray car. That leaves 39 in here, 39. And then we can do this. We say that 10 women owned a car of another color. It's not listed here, like green or purple or something. And the total is 25, so there must be 15 men. And we're not quite done yet, right? I've got, there's 5 categories here, and I've got 4 of them filled in, so I can figure out what the last one is. So I got 26 plus 45 is 71 plus 17 is 88. So there must be 12 men who own white cars. And we can use that to deduce that there's 18 women. And then that'll give me whatever this last thing is. So what do I have there? That's 42 and 39 is 81 and 10 is 91. So that must mean this is a 9 and then this is a 20. And we can check to see that everything works out. So I have 41, 71, 155, and 45 is 200. So that's great. 42 and 48 is 90 and 10 is 100. That's good. At 39 and 54 is 85. No, wait. 29 and 56 is 85. Yes, that's good. And this is plus 15 is 100. All right, so that all looks good. So you can use that that general technique of, if you know the totals, you can go back and piece things together if you're missing parts. I got one on the homework like that. I think it's number 1 or 2, something like that, early on in the homework, just to give you a little, I don't know, thinking experience, I guess. All right, so I want to use that table to find all these probabilities here. Yeah, so this is really just to get us used to the probability notation. So probability of F. So in other words, the probability that I don't want to say this. If I chose a randomly selected person who was in the survey, what's the probability that that person was female? Well, if I go back and look, there were 100 females out of 200 total people. So the probability is 100 out of 200, or 50%, obviously. So this is 100. I'm not going to write the fraction every time. You can also write this as a half or 0.5. Any of those are totally fine. I'm going to continue writing in percents, but you can, if you like fractions better, go ahead and do fractions. If you like decimals better, go ahead and do decimals. I really do not care which one you do. It makes no difference at all. They're all the same number. All right. What's the probability that the person we surveyed owned a silver or gray car? All right, well, silver gray. I'm looking for all of the silver grays. I didn't restrict it to just the men or just the women who own silver or gray cars. So it must be 84 out of 200, which is 42%. All right, now let's do the compound ones. So I've got probability of M and R. So the probability that the person was male and owns a red car. So what I'm looking for there is, I'm looking for where both male and red car are true. So when I look in here, there's only one place where that is, right? So both male and red are true. That's right here. These 11 people are all of the men who own red cars in this survey. So we've got 11 out of 200, which is 5.5%. 5.5%. This one's a little bit trickier, F or W. So I've got the probability that the person was female or that they own a white car. So that means this includes all of the women and then all of the men who own white cars and all of the women who own white cars, right? So this is all the women, and then this is all the people who own white cars, including the men, because I'm looking for F or W. Now, it's a little bit complicated because we are double counting potentially. So here, let me get a different color and start circling things. So F, obviously, that includes all these people here. And then W includes all these people here. But what I don't want to do is just do, well, there's 100 women and 30 people who own white cars. So the answer is 130 out of 200. It's not, because I'm counting those people twice if I do that. Right. So I don't want to think of it like this, where I double circled things. I really kind of want to think of it like this. right? Those are all the people that I am counting. And if we add those up, we can see that it's going to be 112. And I'll show you a quick way to do that. What I did was I just looked at, well, okay, there's all these women, there's 100 women. And then we're also throwing in those 12 men who own white cars, right? So that's 112. It's not 130, it's 112 out of 200. And that's the way you want to think of OR. If it meets one requirement, it's in. If it meets the other requirement, it's also in. And make sure that you don't double count the ones that meet both requirements, because it's still like these 18 women who own white cars, we only count them once, even though they meet both requirements. The question is just, does this person meet one requirement or the other requirement or both requirements? And so, yeah, so this is 112 out of 200, which is 56%. No, I want these in pink. I want to be consistent here. Where's my pink? There it is. There we go. All right, now let's do the trickier one. So OR is a little bit tricky. Given is significantly trickier. So let's look at that. So probability of other given female. So in other words, what is the probability that the person drives a car of another color, given that we already know this person is female? So in other words, I'm only looking within the women. What is the probability of other? So when I go look at that here, oh no. All right, I'm gonna have to erase that line. Hopefully without erasing my tables. All right, wish me luck. Oh, just gets the whole thing. Fantastic. That was easier than I was scared of. Okay. So we're looking only within the women. So I'm totally ignoring the men in this case, right? So we're not looking at these at all. And then within just the women, what's the probability that the person in question drives a car of in the category of other? And it's 10 out of 100, right? So I'm not looking at the 200 anymore. That's not relevant here. I'm only looking at this category. And then within that category, what's the probability? That's 10%, right? 10 out of 100. Do this before we leave the page so I can come back. Oh, where's my mouse cursor? Mouse, where are you at? I think I'm getting old. I can't find my mouse pointer anymore. Nothing will make you feel old like failing at computers. So this was 10%. All right, so now I want to do something totally different, but that looks the same, right? Probability of F given other. So this kind of looks like it might be the same thing, but it's not. Because now it's not that I'm assuming that the person is a woman and then looking at the probability of them driving another colored car. Now what I'm doing is I'm saying, okay, I know the person in question drives a car or in the category of other. Within that, what's the probability that that person is a woman? So that means I'm not looking at all women now. Right now, what I'm looking at is this. Right? Within other, what's the probability that the person is female? And that is 10 out of 25. Right? So 10 out of 25 is 40%. And so that is my answer. Do that. So notice that those are not the same. Given it matters what order you do given in. Conditional probability is not, we would call that symmetric. Okay, so what is the probability of M and B or R? So this is really more an exercise in how to read this. This says, what is the probability that the person that we pick randomly is a man and drives a black or red car? So that means that I'm looking at the men who drive black and red cars. So that is this and this. That's it. So 28 out of 200, which is 14%. And then I got a little bit of trickery here. Not trickery, but just to think about what this means. So what is the probability that someone falls into both the male and female categories in our survey? And we had no overlap between those two. We were putting them in one category or another. And so that means that this is 0%. Can't be both, right? Can't be in both categories in this survey. What is the probability that a randomly selected person falls into either the male category or the female category? Well, that's 100%. Everyone in the survey was one or the other. Realizing now that I may have stepped in a bit of a political landmine there, but we're just going to ignore that. Say we have a very 1950s style survey here. No third options for gender, and no not saying. Okay. So we can also look at like graphs as probability distributions. So this is the table from earlier, just put in graph form. So that is this table right here, right? So I've got grades, A, B, C, D, F, probabilities, 12, 23, 40, 11, 14. And the reason I specifically want to use this is I want to get you used to the idea that probability is area, because it turns out that we're going to use that a lot. So this is pretty straightforward, just probability is area, and we're doing probability notation here. So these are all percentages, right? 25, yeah, these were percentages. So the probability that the grade is greater than or equal, that the randomly selected person's grade is greater than or equal to a C. Well, all I have to do is add up all the things that were C or bigger. So A, B, C, right? So that's 35 and 40 is 75%. So this is 75%. Probability that the grade is an A, given that it is at least a C. So in other words, now I am looking only at these grades right here. Within that, what's the probability that the person gets an A? So this is not out of 100% anymore. Now it's out of 75%, right? Because that's all the area that's over here. So this is 12 out of 75, which is 16%. Yeah, 16%, right? So this is 12% out of the 75% is, so you would just literally make a fraction 12 over 75 or 0.12 over 0.75 if you prefer, and you would get 0.16 for that. Yeah, 0.16. So that is the answer there. Oop. 16%, right? There's a 12% chance that the person gets an A if we're considering everybody, but if we're only considering the C's, within the C's, 16% of, or C or greater, 16% of those were A's. All right, probability that X is less than C. So here, I point this out to make a point. Oop, it's not the, there we go. And the point I want to make here is this. There's a rule called the complement rule. It's very straightforward. It basically says everything is 100%. Probability that X is less than C is just the complement of the probability that X is greater than or equal to C. And when I say the complement, what I mean is this is everything that this is not. So X greater than or equal to C is all these. X less than C is all these, right? And there's no overlap there, right? That we've got two separate categories that take up all the options. We would call that, if we were doing this in an algebra class, a partition, where we're partitioning the grades into two different groups, right? C's are greater, and then D's are lower, right? So basically passing or not passing. And so this first one says, what is the probability that somebody passed? 75%. This says, what's the probability that they didn't pass? Well, that's whatever's left over, which is 25%, right? And you can add up the 11 and 14. Of course, that works out to 25%. That's a totally legitimate thing to do in this case. But I really did want to point out that you can subtract from the total, or you can add up all the parts, right? And subtracting from the total turns out to be really, really helpful a lot of the time. We're going to use that quite a bit, not necessarily right now, but in the near future, that is going to be a thing that we want to keep in mind. So this is, pink, whiteboard. All right, there we go, 25%. And what is the probability that somebody gets an A or a B? Well, that's just, you add the two up. So the reason I wanted to bring this one up was a lot of people get tricked with or and think that and means that you add everything up, and it doesn't. And is more restrictive than or. So if I said the probability of A and B, that would be 0, right? You can't get both an A and a B. Probability of A or B, well, that's 35% because you can get an A or a B. Okay. I want to transition from that into a thing that we're going to be doing a lot of, which is thinking about continuous probability distributions and histograms as well, which are kind of the same thing. So again, I want to talk about histograms and continuous probability distributions. And continuous means, if you remember back from terminology, continuous means anything in a range as opposed to discrete. So something like this, A, B, C, D, F, this is technically qualitative data, but let's say this is 1, 2, 3, 4, 5, right? Where you can only get a 1, a 2, a 3, a 4, or a 5. That is discrete because there's only fixed outcomes that you can get. There's not like everything in a range, right? 1, 2, 3, 4, 5 is not all the things between 1 and 5 because that's only the integers, right? It misses like 1.5, right? So it's missing all the pieces between these numbers. And again, we're going to think of the total area as being 1 all the time. And I really want to emphasize that probability is area. Right? In this visualization that we're using, that is that's our connection between the two. Probability is area. Remember that. We're going to use it a lot. Total area is always going to be 1 or 100% because it's probability. So here's a random histogram that I've got. It goes down from -1 up to 3, and we've got 18, 11, 40, and 25 outcomes in these categories. These are not percentages. This is out of a total of, what is that, 65 and 29 is 94 outcomes. So when I'm looking for a probability here, I'm thinking of 94 outcomes as 100% of the outcomes. So when I find the probability that X is between 2 and 3, oh, and by the way, in my histogram here, if something is exactly 2, I'm including it in the right bar. So in other words, if I got a 2, that would count as being in this bar. If I got a 1, that would count as being in this bar here, not that one. I bring that up because that's why the or equals are here, right? So the probability that X is between 2 and 3 is the way I want to read this. You can read this as 2 less than or equal to X less than 3, but that's super awkward. It's way better to say that X is between 2 and 3. That is 25 out of 94. And I don't have a calculator handy, so this is 25 out of 94. So we're just going to leave it as a fraction for right now. We can go fill in those percentages later or not even bother. Probability that X is greater than or equal to 0, well, that is all of this, right? So that is, what is that, 65, 76 out of 94? Then we've got a nice or here. X is less than 0 or greater than or equal to 2. So here I'm looking at this bar here and this bar here, and that is 43 out of 94. That's basically all there is to it. Is that all I want to say? Yeah, that really is all I want to say. Some histograms are given where the bars are in percentages, which makes this even easier, right? You don't even have to guess what or you don't even have to do the division yourself. You just add up the percentages and there you go. Last one I want to talk about is this. This is similar to a distribution we're actually going to use called a exponential distribution. So here I've got two different pieces of information that I'm starting off giving you or giving us, which is this. And so this says the probability that x is less than 3 is 0.4. So that actually means that there is 0.4 in here, in this region here. Let's do this in a couple of different colors. And I've also said that the probability that x is less than 8 is 78%, or 0.78. So that means that all of this stuff is 0.78. So this is a 0.78 is this. Right, and so notice that that overlaps, of course, which is intentional. And we're going to have to use that information to figure out all of the other things that we want to figure out. So, building on that, I know that if x is less than 3, the probability of that is 0.4. So the probability that x is greater than 3 is the rest of that. So I know the total here, the total area is 1, or 100%. And so if this is 40%, then this must be 60%. Right? Similarly, for the probability that x is greater than 8, well, probability that x is less than 8 is 0.78, so the probability that x is greater than that will be 0.22, or whatever's left over. So this is sort of the first instance of us kind of needing to use the complement rule, where since we know that x is less than 8, probability that x is less than 8 is 78%. Well, that must mean that the other stuff is 22%, right? It's whatever's left over. All right, a little bit tricky here. Probability that x is between 3 and 8. Okay, well, if all of this yellow probability is 78% and the blue part is 40%, that must mean that there's 38% here in the middle, right? Sort of the same as the complement rule, right? You can, if I know this is 40% and the total is 78, well, then the remainder must be the remaining amount, which is 38%. All right, now we got the probability that x is less than 3 or greater than 8. So this stuff, x less than 3, and then this stuff where x is greater than 8. Well, we know that this bit in the middle here is 38%. So the total of the outside stuff must be 62%, the remaining amount. I believe that was my last example. So let me make a quick comment here. You might be thinking, hey, what about the or equal to's that like you had in the last one? Well, it turns out this is kind of funny, and I'll just make this sort of a quick aside, but the area of one particular line is 0. So if I'm writing this out this way, because we are thinking very specifically of probability equals area, and this line has no thickness. So the area of this line is 0. And so it has no probability. So in a continuous distribution like this, less than, or equal to are the same, essentially. But from a mathematical perspective, they're the same. And greater than, or equal to are the same as well. So less than 3 and greater than 3 really are just complements of each other, because right on 3 has 0 probability. Now, this leads to some funny things that I don't want to get into here, like, well, isn't 3 an outcome? How can the probability be 0 if 3 is a possible outcome, right? Doesn't 0 mean impossible? Kind of. There's some problems with 0 and infinity when you start dealing with when you start mixing them in real world contexts. So I'll just say that that's a little bit of a mathematical curiosity, but this really is the way we want to think of this. Okay, I believe that was the last thing I wanted to say. I was thinking there was something else. No, I think that's it. Actually, you know what I'm going to do? I'm going to go ahead and pause the video for a second and go check to make sure that's all I wanted to say. There actually was one other thing I wanted to show you, which is, I don't know if you noticed, but I can subtract from 100 really easily and quite quickly. And so I kind of wanted to show you how to do that. It's a skill that's actually really useful. And it's not just 100. It actually, there's anytime you are subtracting from like this, like let's say I'm going to do 1 million minus 786,154, something like that. This would be really easy as well. Here's the thing you want to see. When I do this subtraction, what I end up doing is borrowing, right? We have to borrow for every one of these digits, right? And so we can think of it like this, right? So this is going to be a 10. Right? So how do I want to do this? This is a 10. Right, and then this right here would be 9,999, basically. Right, that's how we do the borrowing. So this is going to be a 6 and a 4 and a 8 and a 3 and a 1 and a 2. Right, so there's your answer. So the way I see it, so let me do this again. 0, 0, 0, 0, 0, 0. 786,154, comma, comma, comma. So what I'm saying to myself when I do this subtraction is not, let's do the borrowing. What I'm saying to myself is 9,999,910, because that's what I want these things to add up to, right? So I want whatever I put here to add up to 10 with that, with the first digit. And then all the other ones are 9s, right? So 4 and 6 is 10, and then 9, so we got 4, 8, 3, 1, 2. Done. So what I'm doing when I do like 100 minus 67 is I'm saying to myself, I want a 9 for this digit, or a 10 for this digit, and a 9 for that one. So it's going to be 3 and 3, so 33. Right, so when I subtract, I'm going to end up borrowing. This one is going to be coming out or subtracted from a 10. This is going to be subtracted from a 9. And you can do this with any number of digits as long as you're subtracting from like a million or a billion or 100 trillion or something like that, right? Like a 1 followed by a bunch of zeros, you want it to be 9,999,999,910. That's what these things add up to, right? 7 and 2 is 9, 8 and 1 is 9, 6 and 3 is 9, 9, 9, and these add up to 10, and that's it. So anyway, that's the last thing I wanted to show you. And this subtracting from 1 comes up a lot, and so that trick turns out to be surprisingly useful. So there you go. That was the last thing I wanted to say. So I will go ahead and end the video now, and I will see you guys in the next one.